12:03. I think we should start. Hello, everybody. Thank you for attending DecisionCAMP session. This is the last session of this year, and I am proud to present Helmut Simonis, who is a well-known researcher and practical developer in the area of optimization and constraint programming in general. Helmut was one of key developer of one of the first constraint solver, and then he did a lot of real-world work for different major corporations and developing optimization models and using different constraint tools from Prolog to different open source constraint solvers. And these days, Helmut is one of the most known researcher in area of constraint and linear programming, and he used to be a president of Association for Constraint Programming, and I was happy to work for 5 years. My office was next to Helmut office, and I remember this is one of the most interesting time when we work together. And today Helmut will address a very challengeable problem what we all in decision management community interested to address. When you're not building your models manually, but when you try to discover models from your historical data, from positive and negative examples, and usually it works pretty well when you have a more limited environment, more domain-specific environment, like constraint programming is one of them. It's not limited, it's probably one of the most challengeable environment, but still we know what to expect. There are several known concepts, and Helmut and his colleagues take advantage of this fact. And today he would present us his initial results. Helmut, please go ahead.
Okay, thank you very much, Jacob. Thanks for the invitation. A pleasure to talk to a slightly different audience about this. So we're going to talk about learning constraint models from positive and negative examples. And the takeaway points are that we have a way of learning the models from the data. There are some questions about the use case, and I'm going to try and describe a reasonable use case for that. What we want to have is a transferable executable model. So something where we learn from some data and then we can apply that to different data of different sizes, different input variations. We have developed a benchmark set for this type of problem, and we use that at a workshop on the progress towards the holy grail of programming this year. And my system, the CUT system, basically shows the feasibility of the approach, but still it's early days in doing this. The background of this is that I'm working in the Assistant project, which is a Horizon 2020 project of the EU, and constraint acquisition is part of the work package 4 about planning and scheduling. And what we want to demonstrate there is that constraint acquisition can be relevant in a real-world scheduling setting. And we have some case studies from Siemens Energy and Atlas Copco that we are using basically as the motivating examples. But okay, I'm not going to talk about those examples today. This is more introductory level of presentation. So what's constraint programming? If you're not familiar with that, it's a declarative way of solving combinatorial problems. You have an abstract problem description in terms of variables and constraints, and then you have a generic problem solving tool that is using different techniques, and different solvers have different emphasis there. And you get very strong results for scheduling, for rostering, product configuration. These are areas that constraint programming works very well. And as an AI tool, one of the advantages is that this is inherently explainable because it's a logic-based tool. So you basically understand why the system is doing certain things. Okay, now we are not talking just about constraint programming, we are talking about constraint acquisition. So what's that? We basically want to learn constraint models from data, and we are giving positive and negative examples. This is what is called passive learning in the AI context. There is another branch of constraint acquisition that deals with active learning, asking questions to users and having an interactive session with the user. I'm not really very keen on that. Perhaps we can discuss that later on. And constraint acquisition in general is useful to understand a problem and to classify examples as solutions or non-solutions that you haven't seen before. But fundamentally, what you want to do is you want to generate a model and find solutions to new problems. And here's some literature. There's a survey article here from artificial intelligence by some of the people involved, my boss, Barry O'Sullivan, as well. And then there are some earlier papers. This is probably one of the very first ones about constraint acquisition by Jean Freuder and others. And the last one here is by Nicola Beliciano and myself. And we are working in the assistant project together as well about the model seeker, which is one of the fundamental basis of the tool that I'm describing today. Okay, what is a problem with constraint acquisition from my perspective is that there are many different approaches that are studied in the literature, and it's not based on a common use case. And I found that rather disappointing. So it makes a comparison of results, for example, very difficult. So what we tried to do this year is develop this challenge for the Holy Grail to shape the discussions, to come up with a common benchmark set, and then compare tools based on these benchmarks. And here's an example of what constraint acquisition would be doing. And this is about Sudoku. I hope you know what Sudoku is. It's one of these puzzles you find in the newspaper. What you would have as input data would be examples. So you have an example here of a 4x4 Sudoku, a solution and a non-solution. And you have an example of a 9x9 Sudoku and a solution, non-solution, perhaps more than one. And what you would do is you feed that into the constraint acquisition tool, and this comes up with a model, and it says, well, every row must be all different. The values must be different from each other pairwise, and for every column and for every block. So that would be the model that you generate. You pass this to a solver, and you can create a new solution, an extra solution. And that is actually the use case that you would normally have in practice. But you can also use it as a classification tool. So you can use the constraint acquisition to classify tests. And basically, if you give it some new examples, perhaps of an unseen size, it says it's a solution, this is not a solution, this is not a solution. And that can be useful as well, but it also is a good way of exploring what your constraint acquisition tool is able to do.
Helmut, may I ask you a question right here when you go back? This, when you set model, for, who discovers this rule? Each row different, or each columns different? This is automatically discovered rule, or it's manually introduced to the model?
No, this is automatically done. I'll talk about that a little bit more, but there's no human interaction here at all.
Okay, perfect.
It basically finds this. Obviously, the constraint acquisition tool that I describe has a concept of a matrix and of the rows and the columns. So it knows about certain things. If you give it a triangle of data, it will not know what to do with that. There are certain fundamental concepts that are built in. But these are the kind of standard things that you have in mathematical programming, vectors, matrices, numbers, and the constraints that go with that. Okay. And if you actually look at the model that is generated in this case, so this is actually a generated model. This is in a language called MiniZinc. This is from Australia, from Melbourne. And this program here is generated by CAP, by my system, and it basically has some input definition, and then it defines a matrix of variables which have a certain domain, a certain range of possible values, and then it has a set of constraints, one for each row, one for each column, one for each block. And then you're saying you want to find a solution that satisfies the constraints. And that basically is an executable model. You can actually run this through the MiniZinc system, and it will find you a solution.
I will interrupt you again. This is a automatically generated code.
Yeah.
That's not manually created. And what was predefined here, matrices and operators, indices, and including all different constraints?
Well, it knows about global constraints. So it knows that there is a constraint called all different and that it has a certain meaning. And it knows about domain variables. It knows about arrays and vectors. And it knows about some constructs, but again, I'll talk about that a bit more in the talk. But yeah, this is 100% generated, as is this. So the system does not just produce the program; it also produces a textual description of what problem it is solving. So given an integer parameter size, find an assignment for a matrix X with n square size rows and n square size columns, where each element ranges between 1 and n square size, such that the elements of each row are pairwise different, the element of each column are pairwise different, and the elements of each major block are pairwise different. And again, this is generated automatically. And this would be the basis for, let's say, discussion with an end user who doesn't know about constraint programming, doesn't know about the constraints, but he might understand the textual description. Okay, so the intended use case is that we take the input data of a problem, the solutions and non-solutions, the examples that are given, pass this through the constraint acquisition, generate a generic model, run that model with some unseen input through a solver, and get a solution. And the user can influence a little bit what the constraint acquisition is doing, and perhaps he can eliminate some of the constraints, saying, oh, no, I don't really believe that this is true. But in principle, the user looks at this and says, yeah, I like this, I don't like this. You have basically built a program here that can solve new problems of the same type as the ones that you have learned from. And what we want to do is we want to demonstrate that this is feasible, not just for Sudoku, but for more complicated things as well. Okay, so some of the properties that we need to have is the generated model must be transferable to new data. So it's not enough if we just learn from the examples to solve the examples. They are already solved, so there's nothing new there. Obviously, the problem size varies from day to day. Let's say in a scheduling problem, the orders are different every day and the number of orders. You may not see all the variables of the model, and you may have to invent some of those or deduce some of those because the user does not actually include them in the solution. And fundamentally, we assume that the constraints are there for a reason. They're either there because of the structure of the problem, like in the Sudoku, or they're due to the input data that you're giving. So if you have a graph coloring problem, then you would expect that you are given the graph to color as input data, and you have to recognize that as input data, that this is a graph, and that what you want to do with this is do a coloring. And in the challenge, we basically provided a number of these scenarios, 15 instances, and the user basically then has to do the constraint acquisition and solve some classification questions that we were asking, or and or can provide extra solutions, which basically are solutions that are not in the examples that were given. And that then produces a score that says how good are you in understanding and solving the problems that are given. And we'll come back to that in a moment. And here are the problems which were in the first set. And you'll see that most of those are kind of puzzles and smaller kind of problems. But okay, there's graph coloring, there's warehouse location. There are things like BIBDs, so block designs, which are important for experiment design. Costas array, again, has some applications in experiment design. Orthogonal Latin squares, so more combinatorial structures. And these things were basically presented as the challenge problems. And so you're given solutions and non-solutions, but you're not told what problem it is. And the question was, can you actually find out what these problems are, what the constraints are, and then try and find new solutions. So how do we do this? I now describe the CAD system, so my own tool that I've developed recently. What we are trying to do there is we're finding constraint models based on global constraints, which are comparable to hand-built solutions. So they should look like a program I would write myself. That's the idea. The assumption is that all information is either given as data or is part of the regular structure of the problem. And we are doing this, building this bottom up based on the test cases. And at the moment, we are trying to extend this to the scheduling domain. I think next year we'll have some first results on job shop, flow shop type of scheduling problems. Okay, this is the overall architecture, and okay, you will say that is a bit too complicated. Well, there are quite a few things that are happening here. We'll not go into the details, but another example, here we have BIBD, so balanced incomplete block designs, and this is an example solution given as a matrix of 0, 1 values. And in addition, you get some input data saying lambda is 2, b is 6, and k is 3. You're not told anything more. It doesn't have to be called lambda. It could be called Toto as well, if you want to. And you're giving different instance sizes of these kind of problems. So what we try first is we are trying to acquire a size-specific model. And for this, we are basically using the examples, the input data that are given here, and we have a pattern generator that looks at possible pattern of applying constraints, and the constraints come from the global constraint catalog, which is a searchable kind of electronic catalog of all the constraints that people have defined in the past. And from that, we are trying to find the patterns that are used, and that gives us a size-specific model. We can check that with the negative examples to see how good it is at rejecting the negative examples, and we can use it also to predict results applied on the test cases. So if we do this on the metrics that we are given, we have here different patterns that we apply. So a first pattern would say, well, take all the values that are in the matrix and see whether there's a constraint that applies to all these values, or to something which is indexed by an index set, or something where for every row we have a constraint. So the same constraint applies to every row of the matrix, or to every column, or to every block, or to the diagonals of the matrix. Or things where you're saying, okay, I have 2 rows, and perhaps they are consecutive ones, and there's a constraint between these 2 rows, or they are ordered rows. So the second one is always has a greater index than the first one. Or for every pair of rows, we do something. Or we have, again, something based on the matrix where we are given really a matrix of values, not just a set of values like in the first case here. Or we have a transposed matrix and we apply things like this. And then we have the next level where we take two matrices and we're saying, well, we have a constraint between matching rows or matching columns of the two matrices. In our BIBD case, we only have a single matrix. So these are basically all the patterns that we are going to try. And we are finding things like that the sum of the values in each row is equal to 5. And the sum of all the values in each column is equal to 3. And that the scalar product of two different rows is equal to 2. And sum and scalar product are global constraints that are in the catalog. So we know about what these things mean. And these patterns are the patterns that we have defined. And these are the arguments that we observe. So this is the model that we come up with. And there are some other things that hold. And if you are into constraint programming, you will think, yeah, I know this. These are symmetry breaking constraints that are applied to basically reduce the number of solutions that you need to look at. Well, this would be a size-specific model. In the next step, we try to generalize that. For that, we take the size-specific models, pass that through Generalizer, and do some model reduction. And at that point, we also have to do a formula generator to explain the parameter values or to predict the parameter values for new sizes. And that gives us the generic model. And if we do this in our example, we have to introduce basically these extra arguments for the row sum, the column sum, and the scalar product. And we now have to find formulas that explain the observed values that we have seen for the different sizes in terms of the other values and parameters that are given. And sometimes we can eliminate some of the constraints because they only hold in some of the examples. They don't hold in all of the examples. And then we have a model reduction step, which says, okay, I'm only interested in interesting constraints, and I'm going to throw away all the constraints that I'm not really interested in. And there is a concept there of what is interesting constraints, either MiniZinc or a natural, and we can pass that MiniZinc program to a backend solver, so to the MiniZinc system that interfaces to different solvers and produce new solutions that way. We also produce a report which explains what we are doing so that people can understand why certain constraints are there. Okay, underlying all this is a graph-based constraint model where we have a matrix here of our variables, and we have the parameters here, the number of rows and number of columns and the domain. And we have observed that the values in our matrix are always 0, 1. And we have here a formula lambda some p of v divided by p of k, and that is basically the formula that explains the number of columns. And then we have the different constraints that apply with certain patterns. So we have the sum constraint applying to all rows, and it has another parameter, which is another formula of the basic parameters. The generated code, again, this is the thing that is automatically built. There are some formulas which are generated, and they use the input data that are given as the description of the different cases. We have our variables and we have our constraints. You see the sum constraint and the scalar product that we were talking about. And again, we are trying to find a feasible solution. We do deal with optimization problems as well, but in these cases here, we're only interested in finding a feasible solution. There's no objective. And here's the textual description. And okay, this is something that, again, needs a little bit more time to understand, and you have to look up certain things. Some of the constraints are not explained in natural language at this point in time. We'll have to add a little bit more in the global constraint catalog to allow that. We have started with that, but it's not complete. And okay, how does this work on the problems that we were giving in the challenge? Here we have 15 of these problems, and what you can see, we are very, very good at classifying the examples, the positive and the negative samples, and the tests. We achieve 100% accuracy on that. This is perhaps, it looks more impressive than it is, because achieving something like 85, 90% accuracy is relatively straightforward if you have just some basic constraints and some basic patterns. The system is also able to produce extra solutions in most cases. There are 2 cases where it was not able to do that. For the Golomb ruler, basically, it could not generalize the domain bound, and that is understandable because that is the objective function of the Golomb ruler. And for the last problem here, the model is incomplete. We did not find all the constraints, and things were slightly missing in the solutions that we provided. Okay, so what is this all about? What have we done? Well, I've given you some examples of constraint acquisition, which allows us to generate models from examples. And as an area, this is an area of active research. There are many different approaches, but they are hard to compare. So what we were trying to do was defining a realistic use case. So the use case is that we want to take the models that we have learned and apply them to new data and find solutions to these new problems. And I think that is a use case that most people can subscribe to. The results on simple problems show quite a lot of promise. I'm already one step further. I've defined a second set of problems more oriented towards operations research and scheduling. And we are doing very well on those as well. We are currently working on some realistic examples. So some actual scheduling problems from industry, trying to see whether we can actually learn the models in this case. And then have
some technical issue on my side also. So I would ask probably question. Hello? Hello?